I apologize that one of the PowerPoints was just uploaded this morning. I will try to make sure that they are, for Thursday, all of the PowerPoints are uploaded in a timely fashion. And try to get on top of things. Okay. So we actually touched upon some of these concepts yesterday in the laboratory, but we really didn't get into the reason behind some of these concepts. And that is, we're going to start talking about the physical properties associated with liquids. And to talk about the physical properties associated with liquids, we have to get into intermolecular forces, also known as IMFs. Basically, an intermolecular force is going to be the force that holds a solid or a condensed structure together. So a solid or a liquid. It is determined by the structure of the particle, and meaning that we're going to have to apply knowledge from College Chemistry 1 related to the VSEPR shapes, related to the polarity of molecules, in order to be able to determine what type of intermolecular force a substance possesses. Now that I'm going to give you some cues that you can look for to help you figure out more quickly what the intermolecular force is, so that you don't have to draw the Lewis structure, you don't have to determine the VSEPR shape, but at the same time, I do want you to understand it is that shape of the molecule and the polarity of the molecule that ultimately determined whether the molecule, or what type of intermolecular force the molecule has. Now, with intermolecular forces, they originate from interactions between charged particles, meaning that you have a dipole of some sort, meaning you've got one end that's positive and the other end that is negative in the molecule. Now, you can have a permanent dipole. Permanent dipoles occur in ionic compounds where you have a cation, which is permanently positive, and an anion, which is permanently negative. Permanent dipoles occur in polar molecules where you have an end that is permanently positive and an end that is permanently negative. But we can also have what are known as temporary dipoles, which will occur in nonpolar molecules. And these temporary dipoles occur due to the movement of electrons. We cannot think of electrons as being stationary, essentially. You've got to think of them as being something that is in constant motion. So again, intermolecular forces is going to be this attraction between one molecule and another molecule in a condensed state. It is not a bond. It's not a covalent bond or an ionic bond. It is simply an attraction between two different molecules. It's going to be determined by the structure of the particle. Is it polar? Is it nonpolar? Is there a permanent dipole or is there a temporary dipole? And it originates due to interactions between charged species. Now, there are four intermolecular forces that we're going to talk about. The very first one is known as a dispersion force, or sometimes referred to as London dispersion forces. I think I typically use the term London dispersion forces. So if you are watching the flipped classroom videos, you'll hear me use the term London dispersion force. The second type of intermolecular force we're going to talk about is going to be a dipole-dipole force. The third is a hydrogen bonding force, and the fourth is an ion dipole force. These are actually arranged in order of increasing strength of intermolecular force. What I mean by that is hydrogen bond, if a molecule can hydrogen bond, that intermolecular force is going to be stronger than if it simply had dipole-dipole forces. If a compound can hydrogen bond, it's going to have much stronger forces than if it simply had dispersion forces. Now, don't get into this habit of thinking, oh, it only has one force. No. As we're going to talk about, London dispersion forces occur in everything. Dipole-dipole forces and hydrogen bonding occur in polar molecules. So you have to have that one extra step in order to get to these two. With hydrogen bonding requiring a very specific covalent bond in the molecule. So we have to have yet one more criteria to get to the hydrogen bonding. But basically, these intermolecular forces, as we're going to talk about, are going to increase in strength as we go down this grouping. So again, let's break down each of these forces. Let's start with dispersion forces. Again, electrons are in constant motion. Here we have a picture of a helium atom. The helium atom has one electron on one side of the nucleus and one electron on the other side of the nucleus. Okay, that is what we pretty much expect for our helium atom. But these electrons are in constant motion, so sometimes this electron may be here, sometimes it may be out here. But in this example, in frame 2, we still have the electrons on opposite sides of the nucleus. But they are in constant motion. And sometimes those electrons are going to wind up on the exact same side of the nucleus. If those electrons wind up on the exact same side of the nucleus, then we have an electron-dense area and an electron-poor area. Because we have an electron-dense area, now we have a partial negative because electrons carry with them that negative charge. And if we have an electron-poor area, that means it's going to have a partial positive charge because there's no electrons there. This is what causes the dispersion forces. Most of the time, the electrons are on opposite sides of the nucleus. But because electrons are in constant motion, they can wind up on the exact same side of the nucleus and cause this temporary dipole. Questions so far? By the way, I've had some of you, I haven't had many of you though. Please, if you feel comfortable, ask questions. Do not wait until that moment passes you by, because if you have a question, it's likely one of your classmates has a question. Now, if you don't feel comfortable, write that question down so you can send me an email. But if you do feel comfortable, please speak up and ask those questions so that I can answer those questions. So again, a dispersion force is a temporary dipole. Every single molecule has dispersion forces because every single thing has electrons that are in constant motion. Now, one molecule winds up having these electrons on one side, forming this partial negative and partial positive. All of a sudden, what we have the wave going on at a football game. This molecule forces this molecule to have a temporary dipole, which forces the next molecule to have a temporary dipole. Or in other words, we go boom, 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 boom. Now, because electrons are in constant motion, this does not last. That's why it's called a temporary dipole, because these electrons are going to move so that they're on opposite sides of the nucleus, and this partial positive, partial negative is going to go away pretty much as fast as it formed. But it caused a ripple effect through the rest of the molecule. Again, every single molecule, every single atom, including your noble gases, which are unreactive, have dispersion forces. They have dispersion forces because electrons are in constant motion. And since electrons are in constant motion, there is going to be a time where the electrons wind up on one side, and then they force every molecule within the substance to have a temporary dipole. Because it is temporary, it is weak. Because it's only temporary, it is a weak force. And understanding the strength of these intermolecular forces is going to be important when we start talking about physical properties. Now, when we look at the molecules, again, every single molecule has some sort of dispersion force. And what you will notice is as you go down the noble gases, you would, because they have more electrons, there is a greater chance for these dispersion forces to occur. Because you have more electrons, what we see is as we go down the group of noble gases, our boiling point increases. So there is a direct correlation between the size of the molecule and the boiling point. Yesterday, in the lab, we talked about molar mass of the alkanes and how that impacted boiling point. And as we increase the molar mass, we increase the boiling point. The same thing goes here. But you have to be very careful with molar mass. You have to be very careful with molar mass. You have to compare similar substances, whether they are your noble gases or whether they are straight chain alkanes. Because we can have molecules that have a similar molar mass, but and they have widely different boiling points. An example would be what is known as N-pentane. N just means that all of the carbons are lined up in a row. And we said pentane yesterday, pent meant 5, so we're talking a 5-carbon chain. N-pentane has the exact same chemical formula and the exact same molar mass as neopentane. Neopentane, however, has 1 carbon that is single bonded to 4 CH3 groups. Now, in the previous slide, I made the comment that the size matters. We can't rely on the molar mass. It's really about the size. Because if we put N-pentane, 2 N-pentanes in together, there is a lot of opportunity for dipole forces to occur. Because it's this long, flat, pill-shaped molecule. But neopentane has a very small area where those intermolecular forces can occur. Because it is round in shape rather than pill-shaped. It is a circular shape. That difference in shape, where one is larger than the other with respect to the amount of intermolecular forces that can occur between the molecules, is the reason that N-pentane has a boiling point of 36.1 degrees Fahrenheit, whereas neopentane, it's degrees Celsius. Whereas neopentane has a boiling point of 9.5 degrees Celsius. Same exact formula, same exact molar mass, but because the shape is different, the boiling points are different. Questions?
So we have to draw the Lewis structures to figure that out before we do a question, Johnson.
So the question is, would you have to draw the Lewis structures to figure this out? Technically, yes, but technically only on homework where you have to worry about getting the Lewis structures. On an exam, if I wanted you to tell me which of these had the higher boiling point, I would give you the structure to start with. There's only so much time on exams. So again, every single molecule, every single substance has dispersion forces. The strengths of those dispersion forces are based off of the size of the substance. The larger the size of the substance, the greater those dispersion forces will be. The greater those dispersion forces, the greater the boiling point and melting point. And it is because the larger the electron cloud, the more easily it is to polarize that cloud, creating that temporary dipole moment. And again, dispersion forces are temporary because it's all based off of electron movement. Where are the electrons? Okay, so that's dispersion forces. The next strongest intermolecular force is a dipole-dipole force, and then hydrogen bonding. However, dipole-dipole forces and hydrogen bonding require that the molecule be polar to begin with. Dipole-dipole forces and hydrogen bonding require that the molecule be polar to begin with. So I'm going to take a moment and do a little review about polarity. And as I do so, I will give you a few cues to help you more readily determine whether a molecule has hydrogen bonding or whether it's simply a polar molecule. So, if we go back to the discussion of polarity in College Chemistry 1, and we look at the molecule HF. HF is a polar molecule because hydrogen has an electronegativity that is less than fluorine's electronegativity. It's significantly less than fluorine's electronegativity. And therefore, because fluorine is more electronegative, it means that the electrons spend more time around the fluorine. That's what the red symbolizes. And less time around the hydrogen. That's what the blue symbolizes. We therefore have a dipole moment, which is what this type of arrow symbolizes, that is towards the fluorine. Carbon dioxide is a nonpolar molecule. The carbon-oxygen bond is polar. The carbon-oxygen bond is polarized towards the oxygen. But carbon dioxide itself is nonpolar because the two dipole moments cancel each other out. Water is a polar molecule. It has your hydrogen and it has your oxygen. The hydrogen-oxygen bonds are polarized towards the oxygen because the oxygen is significantly more electronegative than are the hydrogens. But in this case, the polarization of the bonds are additive. They both merge onto that oxygen, making this molecule polarized towards the oxygen. Meaning that the oxygen has a more negative area and a more positive area on the hydrogens. Hydrogen chloride is also a polar molecule. The hydrogen is less electronegative than the chlorine. Because the hydrogen is less electronegative than the chlorine, the electrons spend more time around the chlorine. Since the electrons spend more time around the chlorine end of this molecule has a partial negative, a permanent partial negative. And the hydrogen, because it has less, the electrons spend less time around the hydrogen, has a permanent partial positive. Dimethyl ether is also a polar molecule. It has, if you look at the carbon-oxygen bond, the oxygen is significantly more electronegative than the carbon. Because the oxygen is significantly more electronegative than the carbon, the electrons are pulled towards the oxygen. Now, when this molecule is drawn in the correct shape, what we see is we have a negative end of the molecule. We have a partial negative end of the molecule. And all of the hydrogens make up a partial positive end of the molecule, therefore making this molecule polar. So, just as a reminder of electronegativity, fluorine is the most electronegative atom on the entire periodic table. Francium, element number 87, is the least electronegative atom on the entire periodic table. Electronegativity fans from fluorine. So pretty much if you see nitrogen, oxygen, fluorine, chlorine, you can guarantee those molecules are going to be polar. Because those are some of the most electronegative atoms on the entire periodic table. You see nitrogen, oxygen, chlorine. Those are you can guarantee those are gonna be polar because they are the most electronegative atoms on the entire periodic table. Now, if you have a permanent polar molecule, it means that you've got a permanent positive end and a permanent negative end to those molecules. Because you have a permanent positive and a permanent negative, it means that our intermolecular forces, the attraction between molecules, well, now we got a magnetic force. Because if I think of two magnets, a magnet has a positive and a negative. My other magnet has a positive and a negative. The intermolecular force is the force between those two magnets. So if I have a permanent positive and a permanent negative, and another permanent positive and a permanent negative, they're going to line up. So dimethyl ether. Again, the oxygens were negative, and the carbon hydrogens were positive, making a permanent negative and a permanent positive. They're going to cause this nice effect where the next molecule that has a permanent positive and permanent negative are going to align. So that this is your intermolecular force. It is the force between the negative and the positive on the adjacent molecules. All polar molecules have dipole-dipole moments. All polar molecules have dipole-dipole moments. And therefore, they all have dipole-dipole forces. So far we've talked about dispersion forces. All molecules have dispersion forces. But dispersion forces are the result of a temporary dipole. Non-polar molecules, dispersion forces is the only force that they have. Then we have dipole-dipole forces. Dipole-dipole forces require a polar molecule. How big of a factor is this? Well, this is a table or a graph of 5 molecules that have similar molar masses. Propane has a molar mass of 44.09 grams per mole. Dimethyl ether has a molar mass of 46.07 grams per mole, meaning there's not a huge difference in the molar mass here. Ethylene oxide has a molar mass of 44.05. Hey, it's almost the exact same as propane. Acetaldehyde, 44.05. Hey, it has almost the exact same as propane. And then acetonitrile has 41.05. It's actually got a lower molar mass. But if you notice, these 5, those 4 have higher boiling points than this propane. That is because propane has only dispersion forces. Because propane is a nonpolar molecule. has dimethyl ether, ethylene oxide, acetaldehyde, and acetonitrile, you'll notice has a polar negative end and a polar positive end, a permanent dipole. Because these have permanent dipoles, their boiling points will be higher because they also have dipole forces as well as dispersion forces. Folks, this whole polarity also determines the ability for two different substances to combine, or two different liquids to combine. If two different liquids combine, they're called miscible. And basically, folks, we get into the concept of like dissolves like. Polar wants polar, nonpolar wants nonpolar. If they have different polarities, they tend to not mix, such as oil and water. Oil is nonpolar, water is polar. They don't want to mix. But water and rubbing alcohol mix perfectly because both of those are polar. So again, miscibility is determined based off of this whole idea of polarity. If it's polar, it wants polar. If it's nonpolar, it wants nonpolar to be miscible. Miscible simply means that the two molecules combine to form a solution. Okay, so polar, nonpolar seems to be a big thing because it all determines whether you just have London dispersion forces or whether you also have a dipole-dipole force. So let's talk about ways that we can, some things that will cue us in to whether we're dealing with nonpolar molecules or whether we're dealing with polar molecules. First, as I've said, it comes down to shape. Can you read that in the back? Okay. Nonpolar molecules will include linear molecules, trigonal pyramidal molecules, tetrahedral, trigonal bipyramidal, octahedral, and square planar molecules, where all outer atoms are the same. It also will consist of molecules that contain hydrogen and carbon only, which will be your alkanes, alkenes, alkynes. No matter what the shape, if it contains carbon and hydrogen only, it's going to be nonpolar. Everything else is going to be polar. So that's one way we can distinguish polar and nonpolar. Let's talk about other ways to distinguish polar and nonpolar. If you draw the Lewis structure, and you see that it has a lone pair on the central atom, you can guarantee it is going to be polar. I'm not talking about the outer atoms, the external atoms. I'm just talking about central atoms. Another cue that something is polar or nonpolar. Polar molecules typically have, they'll have oxygen, nitrogen, fluorine, chlorine, sulfur as a central atom. If you see any of those, there's a good chance that we're going to talk about something that is polar. I'm not saying that these are perfect. I'm saying that in general, you can look for these and it'll help you. Whichever you're the strongest at. So the first one, you had to know VSEPR theory. The second one, you had to be able to get to Lewis structures. The third one is the least useful, but as far as guaranteeing something, but it is the quickest way to typically sort molecules. Questions? Okay, so we've talked about dispersion forces. They're in every molecule. Or every substance, I should say. We talked about dipole-dipole. Dipole-dipole requires that the molecule be polar. And hence I've given you some cues to help you identify whether a molecule is probably polar or not. Now, hydrogen bonding is yet a stronger force, but it requires a very specific type of covalent bond to be present within the molecule. Not only must the molecule be polar, but it must have a HF covalent bond in it. Not only must the molecule be polar, but it must have an OH bond in it or an NH bond in it. If it has one of those, if it's polar and it has one of those bonds, now we have hydrogen bonding. If it is polar and it has one of those three bonds, in the structure, then we have hydrogen bonding. Hydrogen bonding is responsible for the miracle that is water. Water being such a small molecule should not have a boiling point of 100 degrees Celsius. The only reason water has a boiling point of 100 degrees Celsius is because of that hydrogen bonding intermolecular force. What difference does it make? Here we have ethanol, which has an oxygen hydrogen bond. So what type of force does it have? It has an oxygen hydrogen bond. So what force does it have? Hydrogen bonding. And here we have dimethyl ether. They have the exact same formula. Therefore, they have the exact same molar mass. But dimethyl ether does not have a OH bond. It has a carbon oxygen bond. Does not have an OH. So what does that mean? Well, ethanol has a boiling point of 78.3 degrees Celsius. Dimethyl ether is negative 22 degrees Celsius, meaning that ethanol will be a liquid at room temperature. But dimethyl ether is a gas at room temperature. And it is because of the intermolecular forces being so different. One has hydrogen bonding, which is stronger, whereas this one simply has dipole-dipole, which is a much weaker force. So anything that has hydrogen bonding, all of a sudden those boiling points and melting points are going to skyrocket. Anything that has hydrogen bonding, the boiling points and melting points are going to skyrocket. Because it has a stronger intermolecular force. Questions? So we've talked about dispersion forces. Everything has dispersion forces, including nonpolar molecules. We talked about dipole-dipole forces, which require a polar molecule. Dipole-dipole forces are stronger than London dispersion forces. Therefore, they have higher melting points and boiling points than does a molecule that only has London dispersion forces. Hydrogen bonding is a polar molecule, but it requires a very specific covalent bond be found within that molecule. It needs an NH-OH or FH bond. If it has an NH-OH or FH bond, all of a sudden the melting points and boiling points are going to skyrocket because it has hydrogen bonding. The last force is only going to occur in a solution of an ionic compound and something like water, a polar compound. It only occurs in solutions of ionic compounds and polar compounds, and that is an ion dipole force. When you take something like sodium chloride and you add water to it, the sodium, being a cation, has a permanent positive. that permanent positive is going to be attracted to the permanent negatives on the water molecules. And so the water molecules surround that sodium and pull it out. This is an ion dipole interaction. The chlorine. The chlorine is a permanently negative anion. It is going to be attracted to the permanent positive of the polar molecule. The hydrogens are going to surround the chlorine and pull it away, making an ion dipole interaction. So again, an ion dipole will only occur in mixtures of an ionic compound and a polar compound. So one of the big things you need to be able to do is determine what IMF is present in molecules. Let's use some of these things up here to help us. N2 is nitrogen triple bond nitrogen. What type of intermolecular force is this going to have? Well, it's going to have London dispersion forces because everything has London dispersion forces. But now what we really need to answer is this a nonpolar molecule or a polar molecule? Nonpolar because it's just the same element. Therefore, this is going, London dispersion forces is the only force that's going to be present. The next one, we have carbon triple bond oxygen. Again, it's going to have London dispersion forces because everything has London dispersion forces. But is this molecule polar or is it nonpolar? It's polar. It's polar where the oxygen has, because the oxygen has a higher electronegativity. Therefore, it also will have dipole-dipole forces. Now, polar molecules will have dipole-dipole, but they also can, if they have the right bonds, have hydrogen bonding. Does this one have the right bonds? No. So that is all it's going to have is London dispersion and dipole-dipole. Folks, some of the stuff that I was mentioning up here really comes into play in this next one. Because right off the bat, I see an OH. I know it's going to have London dispersion. But because of that OH, what is it going to have? It's going to have hydrogen bonding, and therefore it must also have dipole-dipole. The next one. If I draw the Lewis structure, what do I notice on the central atom? A lone pair. So what does that make this molecule? Polar. So it's going to have London dispersion, but it's also going to have dipole-dipole. Does it have anything else? No. And then SiBr4. Is going to be a molecule that has 4 bonds of bromine to a silicon, making this molecule tetrahedral. We know it's going to have London dispersion. Is it going to have anything else? No, because it's a nonpolar molecule. It's tetrahedral and all of the outer atoms are the same. You got to be able to sort this because the questions next are, okay, which of these molecules is going to have the highest boiling point? CH3OH because it has that hydrogen bonding capability. Which two molecule or which of these molecules is most likely to have the lowest melting points and boiling points? Okay, so I heard the answer. It is nitrogen. But what I would know is I would go, okay, it has to be between these two, so I can minimize the number. Then I have to think which is bigger. Because remember, the larger London dispersion forces occur with the bigger structure. So it would be nitrogen has the lowest boiling point. And melting point. Questions? Okay, so IMF, some physical properties. Today and Thursday, we're going to be talking about some of these physical properties. We've already talked about two of the physical properties to some degree, and that's boiling point and melting point. And what we noticed is as the strength of the intermolecular force, that's what IMF is short for, intermolecular force, as the strength of the intermolecular force increases, the boiling point and melting point increase. Now, one of the things that we're going to encounter that I mentioned on Thursday of last week is that the energy required to melt a substance is actually going to be less than the energy required to boil a substance. Meaning, what I mean by this is the energy required to take a solid and make it a liquid, just that one step of solid to liquid, that energy is less than it takes to make a liquid into a gas. And the reason for that is when you go from a solid into a liquid, you are breaking some of the intermolecular forces down, but not all of them. Because a solid, you have that nice tidy array, so you definitely have those intermolecular forces. But when you break that down to a liquid, you still have the molecules close enough together to have fairly strong intermolecular forces. So all we're doing is we're breaking a portion of the intermolecular forces as we melt the substance. Now, as we go from a liquid into a gas, though, if you go back to Thursday's lecture, we got to break everything apart. Meaning we have to get rid of every single intermolecular force. So it takes more energy to boil a substance because you are getting rid of all of the intermolecular forces. We essentially did this question already, which substance has the highest boiling point? They're the same molecule, so we said this one because it had London dispersion, dipole-dipole, and hydrogen bonding available. Whereas carbon monoxide only had London dispersion and dipole-dipole, and nitrogen only had London dispersion. So because of the presence of that hydrogen bonding, CH3OH would have the highest boiling point. It would have the highest melting point too. Now, the second physical property we're going to talk about is surface tension. Surface tension, whoops. Surface tension is described by how tightly molecules are held together at the surface of a liquid. Now, when we think about intermolecular forces, so far all I've shown you is a picture of one molecule attracted to a second molecule. But when you really start thinking about the structure of a liquid, you have all of these molecules, and all of these molecules are interacting together, so that this one on the top, it's attracted to another one on the top. It's attracted to the one on the bottom. And technically, even though it's not shown, this one is attracted to that one. And over here, we'll have one that's attracted to it. So surface tension is based off of those attractions. The stronger those attractions, the greater the surface tension. This is why critters can walk on water, is because the surface tension. So surface tension is also based off of the intermolecular forces. The stronger the IMFs, the greater the surface tension. It's surface tension that is also responsible for why you can continually add, or for a good amount of time, you can add drops of water to the top of a penny and it forms this bowl. It's all based off of surface tension and how well the molecules are pulling on each other. I forgot I put that slide in there. The stronger the IMF, the greater the surface tension. So which compound would you expect to have the greatest surface tension? This compound, by the way, I want to just go over how to interpret formulas for those that don't have that experience. This compound, what it says is attached to this carbon, you're going to find an oxygen and you're going to find two CH3 groups. So this is what the structure of that compound looks like. And then we have water. Which one of these do you expect to have the greatest surface tension? Why? Well, what forces are present? In the formaldehyde? No, not formaldehyde. Because that's an ether. In the first compound, what intermolecular forces are present? Dispersion and dipole-dipole, because we'll have that going there. What about in the water? What forces are present? Dispersion dipole-dipole, and hydrogen bonding. So because of the presence of that hydrogen bonding, we know that water will have the greater surface tension. Another one is viscosity, which we introduced the concept of viscosity yesterday. Viscosity is the resistance to flow. Have to think about it as resistance to flow. From your experience, if you try to pour water and you try to pour honey, which one is more resistant to come out of the container? Honey. That is because the honey has a higher viscosity. Now, why does honey have a higher viscosity? Because it has more hydrogen bonding. It has multiple locations where hydrogen bonding can occur. So honey is more viscous because it has the greater intermolecular forces, because it has more hydrogen bonding locations. So the stronger the IMFs, the greater the resistance to flow, and hence the greater a substance's viscosity. So let's go back to two compounds we saw before. And let's figure out who would have the greatest viscosity. Who would be more resistant to flow? Would it be N-pentane or would it be neopentane? N-pentane. They both have London dispersion forces. But when we look at the structure, N-pentane is a bigger molecule than is neopentane. There is more locations for London dispersion forces to occur in N-pentane than there is in neopentane. Okay. What we're going to start, but I won't get very far, is we're going to start on this concept of vaporization and vapor pressure, which is yet another set of physical properties associated with intermolecular forces. What's the difference between vaporization and vapor pressure? It all depends upon the type of container. Vaporization occurs, period. It is when the surface molecules at whatever temperature have enough energy to escape into gas form. You have vaporization of water at room temperature. You have vaporization of water at higher temperatures. In other words, temperature is not the only factor involved in vaporization. Vaporization occurs, period. It's when surface molecules gain enough energy that they can escape into the atmosphere, the space above them. Now, vaporization can be measured using vapor pressure. But to determine vapor pressure, you must have a sealed container. What happens is some of these molecules in the liquid phase have sufficient energy to break free and go into the gas phase. These gas molecules move in every possible direction until they collide with a surface. When they collide with the surface, a portion of their energy is given off to that surface, and that is where we get our vapor pressure. Now, once they collide with the surface, they are going to move in another direction until they collide with another surface or another substance, where they're going to give off some more of their energy. At some point, the molecule is going to lose enough energy that it will condense back into the liquid phase. So this is what is considered to be a dynamic equilibrium, because the liquid molecules are going into gas phase as quickly as the gas molecules are going into liquid phase. So the rate stays constant for this process. But again, it's vapor pressure because these gas molecules are colliding with the surface and applying pressure. You can only measure vapor pressure in a closed system. With that, I will pick up with this concept on Thursday, and we will deal with the Clausius-Clapeyron equation and hopefully get into heating and cooling terms as well. And I did get your email. I have not read it in its entirety. I read enough to know what it was about, but I understand that, and just communication for me is the key.
You showed us how to, like, I'm trying to take the data from this and this. And you showed us how you should.
Okay, highlight B. Hit for you, it's going to be command. And hold the command down.
Oh.
And highlight D.
Oh, okay. Oh, shoot. I get what you mean though. Thank you so much.
Not a problem. I'm going to write the homework tonight, or basically as soon as I get back to my office. Okay. That is my plan, because now I kind of know where we're going to end up on Thursday. And I didn't want to give you homework that we weren't even going to get to.
Okay, that makes
So,
sense. Thank you.
not a problem. Yeah. Hello. We should get back into the class.